So for problem 2, I think the first step is to make sure that we can understand pretty clearly all of the products which are formed along the way. So here you start out with, this would be, so if it was just that would be benzoic acid. So this would be 4-hydroxybenzoic acid. And then so we're going to treat it with nitric acid, and remember that the operative electrophile in this case is this. Right, and then so then you have to ask yourself, what position is this going to react at? This hydroxy group, this phenol group, is going to be an activating group, right? It has a lone pair that will activate the ring, so that's going to activate at the ortho and para positions. This is going to be a deactivating group. See it there? So that's going to deactivate the system, be a meta director, but it doesn't really matter because all you really care about is if you have an activating group, that is the important thing to look at. Your deactivating groups aren't really important unless they happen to fall on, like let's say that you had a carboxylic acid there, and then you might have some decreased reactivity, but won't really deal with that. Alright, so you have your activating group. It's an ortho-para director. This is your operating electrophile, so you'll get nucleophilic attack, and this will be subsequently followed by the standard mechanism for you get nucleophilic attack, and then you no longer have an aromatic system, then illumination of a hydrogen to give you your NO2 group at that point. So then you treat this with a base, and you treat it with N-propyl chloride. So probably I should have been a little bit more specific here, and I probably should have said like 2 equivalents of base. And then we draw N-propyl chloride. So that's N-propyl chloride. So we have 2 positions here that are acidic. That'll be our first position, and then our second position will be here. pK of this should be, you know, around 4. It'll probably be, it'll actually be a little bit lower. pK of this will be around 10, but again, 2 equivalents of base. And then at this point, the question is, what is the better nucleophile? And hopefully you can realize that, going back to when we were talking about SN2, that this will be the better nucleophile, and it will, there we go, an SN2 type reaction. Ignore the bad arrow trace. So then we get to this molecule, and then treatment of this with thionyl chloride. So that is the standard reagent that is used to take a carboxylic acid and convert it to an acid chloride. Right, and again, I'm not going to, so this is your very standard mechanism for thionyl chloride converting carboxylic acids to acid chlorides, and you can look up that mechanism. So then we come over to here, and so this is, so I had some people ask some questions about this, that this part is separate from this. So once you get to here, that is treated as compound number 4. And then, so then you need to work with this to come up with this product, right? And then that's going to react with 4. So the question is, what is this? Well, this is just a standard SN2 type opening of an epoxide ring. Right. So after that, you go work up. to give us this molecule. So if this is then going to react with this, the question is, what is the most nucleophilic position in this molecule? There is a lone pair here, and generally nitrogens are better nucleophiles than oxygen. However, this is a tertiary nitrogen. So at that point, primary nitrogens are very nucleophilic, secondary nitrogens are reasonably nucleophilic, but tertiary nitrogens are very poorly nucleophilic. And you can kind of understand why, is that if you were to react this as the nucleophile, the net product out of that would have a formal positive charge, right? But if you react here, you can form this ester. And so this is nucleophilic acyl substitution. So right, to give us this, and then our standard reaction conditions for converting an aromatic nitro group to an amine. And that is how you get this local anesthetic.